All right, shall I start? Yeah. Thank you for inviting me to this seminar. It's a great pleasure to speak at Tech, although virtually, but nevertheless, this is the best we can do at this time. And yeah, I'll speak about, that's quite a general title, complex geometry of manifolds with torus section. But more precisely, I'll be speaking about one particular family of manifolds with torus sections, which we've been studying for more than 20 years with several people, including Victor Buchstaber and others. And recently, well, maybe now it's not so recently, several years ago, it turned out that they have some meaning from the perspective of complex geometry. Namely, they possess very interesting complex analytic structures, which are very far from, and therefore they constitute a large family of complex analytic manifolds, which are very different from those complex manifolds that arise from algebraic geometry. They are very far from being projective algebraic varieties, for instance. They're almost never Kähler, and as such, they include, as a subfamilies, most well-known examples of non-Kähler complex manifolds. So we call these manifolds moment-angle manifolds, and there are several motivations for their definition. I'll probably, one is coming from toric geometry, from algebraic geometry of toric varieties, and another coming from symplectic geometry. And basically, that's where this name came from. So I'll start with a symplectic motivation, but then I'll pass to purely combinatorial topological construction, and eventually we'll put on some complex analytic flash onto this construction, and I'll try to convince you that they might be very interesting from this complex geometric perspective. So let's start with a coordinate-wise action of the compact torus, m-dimensional compact torus on m-dimensional complex space. So just the torus acts by coordinate-wise multiplications, and this action is Hamiltonian, so it preserves the symplectic form, and furthermore it has a moment map. Namely, the moment map for this action is given by just well, I think there should be, well, it depends on how you define the moment map, but anyway, that's up to a sign. This moment map is given by as a square of modules of the coordinates. So the moment map takes your space on which the torus acts to the Lie algebra, the dual Lie algebra of the torus.
Taras, excuse me. It's not weighted action. So on each coordinate, just multiply by. Just
multiplying by. So if you have coordinates T1 through Tm here, so you just multiply Zm, Zi by Ti. Without any weights. Yeah. So far, the weights will appear very soon. So now, and now you can. There is a well-known construction, that symplectic construction of toric varieties, if you wish, or they are sometimes called Hamiltonian toric manifolds. So you look at the symplectic quotient. I'll define this in a moment. Symplectic quotient of the complex space by a subtorus. So you look at the closed subgroup inside your m-dimensional torus. Well, let's closed connected subgroup, a subtorus m of dimension, say m minus n, the codimension n. And then you take the symplectic quotient. I'll briefly describe it soon. And in this way, you get a compact manifold with an action of the quotient torus. So it has precisely half-dimensional torus action, and it's a very regular example of a kind of a Hamiltonian system with closed orbits. So it's the best possible Hamiltonian system, the torus action. Well, in more detail, what's the symplectic quotient? You look at this. This is a standard moment map for the action of the Tm, this one. And then you need just to include, so the Lie algebra of the subtorus includes in the Lie algebra of the big torus, and therefore the dual Lie algebra of Rm projects onto the dual Lie algebra of the subtorus, and the moment map is just this composite. So if you write it in coordinates, that's the moment map for the restricted action. If you write it in the coordinates, then you get just that M tuple of complex numbers is sent to a set of M minus N quadratic expressions in those squares of modules. They'll appear in a moment. And then the symplectic quotient is the following construction. So you take a regular value for this moment map. It depends on, there are many choices of these regular values, and the result depends on which one you choose. So you take this regular value and take the preimage of the regular value. So this preimage is a submanifold in CM of codimension so it's a submanifold of dimension of codimension equal to the dimension of this Lie algebra. So it's M plus N, and it's invariant with respect to this K action, to the action of the subtorus, and you take this action is, well, under some additional restriction, it's free. In general, it's only almost free. So in general, you just get an orbifold rather than a manifold. But under some mild assumption, you get that this action is actually free, and then the quotient is a closed manifold. So this is a closed manifold, and it has a symplectic structure. So if you restrict the standard symplectic form on CM, then it's degenerate. But its kernel is precisely the tangent space to the K orbits. So if you take out the quotient by the K orbits, then the form becomes non-degenerate. So in other words, there is a symplectic form omega prime on this two-n-dimensional manifold, such that if you lift it to this level set for the moment map, then you get precisely the restriction of the symplectic form on the original space. So this is a quite standard construction, originally due to Martin and Weinstein, and it has been heavily studied in symplectic topology and also in toric geometry of toric varieties. But somehow we are not going to, so this M2N, the Hamiltonian toric manifold, is quite a well-known object. But what is slightly less known is this intermediate stage, this level set for the moment map. And my point is that it's actually almost equally interesting. So if you look at this level set, then it's not symplectic, of course, because the restriction of the symplectic form is degenerate, but it has somehow very interesting geometric properties from a very different perspective, and it's also very interesting topologically. That was our origins of the study. So it's a very interesting object from the point of view of topology, of algebraic topology. So, but let's look at it from a more abstract perspective. So we have.
Taras, excuse me. This manifold obviously is not symplectic. I'm talking about level set of moment map.
Yes.
But is it Poisson? Is the globally well-defined Poisson structure on it that makes it Poisson manifold?
Well, I mean, I don't think there is a natural. It's in a sense sometimes it's a contact manifold, but I don't think it's Poisson. Well, I mean, it has its dimension is not necessarily even. That's a mild abstraction. It can be made even by some playing with the data. Yeah, but
it's not at all an abstraction for Poisson. Poisson
yes.
be,
Yeah, but so it's. I'm not. I don't think it's Poisson. I don't think it's Poisson. Well, in any natural way. So in a way that this Poisson structure is coming from the torus section.
Okay, thank you.
But I haven't looked at that. It's just, I mean, some other people looked at the contact structure on it, and but they never mentioned that it's Poisson. It's just my ignorance. Yeah, but yeah, I'll show you that it's actually a complex analytic manifold. Also, it's defined in this way. It's defined in a using a procedure which is kind of somehow very much not holomorphic, but in fact it can be modified so that it possesses a complex structure. So okay, so that level set we refer to as a polytopic. Well, I'll tell you in a second why it's polytopic. So that a slightly more general construction which is not related to polytopes. Moment angle manifold. So, as I said, the moment map, it consists of Hamiltonians. Yes, the Hamiltonians for the actions of the m-n dimensional torus, and also those Hamiltonians are just quadratic expression in terms of those square of modules. There are some Hermitian quadrics. And in order to write down this level set, the moment angle manifold in coordinates, you just need to write down a set of quadratic equations in square of modules of complex coordinates, right? So you can write it down explicitly as a subset sitting in your m-dimensional space as a subset given by m-n quadratic equations. But those equations are not holomorphic.
Sorry, Taras, so these gammas are just from the definition of moment map, yeah?
Yes, precisely.
So
those, I'll tell you, they're like they're those gammas which define you as the subtorus in m-dimensional torus, yeah. So,
Taras, in order this subtorus, if you take directions, it has to be with rational coordinates, otherwise.
Precisely, yeah.
So, is there any restriction on gammas? Are they rational or what?
Well, yeah, I mean, if you wanted to, from the motivations, there are restrictions. There must be like a lattice, yeah, but rational. But I mean, you can define this manifold without any restriction. It will not. It won't have any meaning from the symplectic construction. Then, oh well, at least it has some generalized meaning. But so if you define it from a torus, then those things are rational, yes. But you can define it abstractly. This is what I'm going to do soon, without any restrictions on those gammas, yeah. So, namely, if you write it like this as intersection of m-n Hermitian quadrics, then you need only to care about the non-degeneracy of this intersection, so that the set defined by those quadrics is a manifold. It's a transverse intersection. And this is somehow inscribed in the symplectic construction, but if it's not part of the symplectic construction, then you have to impose this condition. So, but if you go back to the symplectic construction, then this level set is invariant with respect to the torus section, and the quotient by the torus section is the same as the quotient of the Hamiltonian toric manifold by the compact residual torus section. So it's just the moment polytope sitting inside the Lie algebra of the n-dimensional torus. So, and you can identify this polytope by just from this quadrics by just taking out the torus. So instead of square of modules of complex coordinates, you just get real coordinates, and you get a polytope as a set of non-negative solutions of this system of linear equations. So if you start with a symplectic construction, this is a moment polytope for the Hamiltonian torus section. And if you write this polytope as an intersection of half spaces with facet normals, then I mentioned that you need to put some condition on the action that guarantees you that the action is actually free rather than being almost free. And this is a Delzant condition from toric geometry or from symplectic toric geometry, that those those things are actually rational vectors. They sit in the lattice in the dual lattice of the n-dimensional torus. So this is a Gale duality between the the phase normals of the polytope and those gammas, the weights of the subtorus. And this non-singularity condition for the freeness condition for the torus section is just the condition that guarantees you that the toric variety is non-singular. So that the facet normals form a lattice basis whenever facets intersect at a vertex. Okay, so now that's all with the motivation, and now we can define it. Just forget about symplectic geometry for a second and define this purely abstractly by just looking at a polytope in n-dimensional space. Well, this is just arbitrary polytope, not necessarily a moment polytope for a Hamiltonian torus manifold. It can be even non-compact, so you can produce non-compact examples, but we'll be interested with compact examples. So polytope for us is bounded. So it's a bounded intersection of half spaces, and it's full dimensional. We assume it to be full dimensional of dimension n. Then, so now, how to define this moment angle manifold abstractly from just arbitrary polytope? You write down a polytope, you write down a map like this. So you just, so this polytope sits as an intersection of half spaces. It sits inside n-dimensional space. And you send a point in your n-dimensional space to m-dimensional space by just sending to the left-hand side of those equations defining your polytope. And in this way, you get a copy of your polytope, a fine copy, a fine equivalent copy of your polytope inside this high dimensional space. So this m is a number of facets, the number of equations here, and n is a dimension of the embed space of the polytope. So usually, for P to be bounded, m has to be larger than n. And in this way, you get a copy of your polytope inside this high dimensional space, and this copy sits as an intersection of an n-dimensional plane with this positive angle. So you can get, that's just simple contact geometry, you can get up to a fine equivalence, you can get arbitrary polytope as an intersection, n-dimensional polytope as an intersection of n-dimensional plane with this coordinate angle. That's how it works. So of course, obviously those, if x is in your polytope, then all those values are non-negative, and therefore you're actually in this positive angle. And now, so here you have this map. So we restrict it to the polytope. So we embed polytope into this positive angle. Now remember that this positive angle can be thought of as an image of the moment map for the standard torus section. But now we just consider this as a map like this, coordinate-wise square of modules. And then you pull back. So you just restrict this quotient map for the, you can think of as the quotient map for the coordinate-wise torus section. And you just restrict this quotient map onto the image of your polytope, onto your polytope. And by looking at the orbit which passes through the points in your polytope, you get a subset in CM. Subset consisting of TM orbits. So it's invariant subsets with quotient the polytope. So to define it, we just need a polytope. So everything else is like constructed from the polytope. You construct a map, and this is a standard map, and you pull back. Yeah, it has to say pullback diagram. So it's a definition of that. It's a restriction. So, and then of course you can say that this ZP is sometimes nicer than in other cases. So namely, it's if you start with a simple polytope, so a simple means that it's generic in terms of the bounding hyperplanes. So the bounding hyperplanes are in general position at each vertex. So at every vertex there are precisely n facets meet. So if this presentation is generic, then you get a smooth manifold from this construction. And this is again just an exercise in Gale duality that one general position condition translates into another. So what you need to do is, sorry, yeah, I need to flip back. So you need, so this somehow you have an n-dimensional plane in m-dimensional space, which is defined parametrically, and you need to write it down by equations. and this is a Gale duality, solving some system of linear equations involved here. And by solving this system of linear equations, you can write down this n-dimensional plane by m minus n equations. Yeah, and then to get back to your manifold in m-dimensional space, you have to replace the real coordinate by the square of modules of complex coordinates, and then you get a presentation of your moment angle manifold by quadrics. This is precisely the presentation coming from the symplectic geometry in case you have lattices and torus sections. And then you need to check that it is not non-degenerate precisely when you started with a simple polytope. So the non-degenerate intersection of quadrics corresponds to generic intersection of half spaces. That's kind of a Gale duality.
Taras, excuse me again. Simple. It's not necessary to be convex.
It's not necessary. Sorry.
To be convex. Is it convex? What is simple?
Yeah, the polytope is convex. Yeah, it's just an intersection of half spaces. Yes.
Mm-hmm.
Yeah, polytope is convex. Yeah, when I say polytope, I mean a convex polytope. Yeah, it's one of two possible definitions. You can either define it as a convex hull of finitely many points or a bounded intersection of finitely many half spaces. Yeah, so we do half spaces definition here. So yeah, polytope is convex. Yeah. And it, moreover, yeah, for it to work nicely, to get manifold, it needs to be simple. So it's just at every vertex you have smallest number of facets meeting. Like a cube, for instance, or a dodecahedron is fine, but icosahedron is not fine, because like if you perturb the bounding hyperplanes of a octahedron, like icosahedron, then those vertices with say 4 facets, they're split into 2 vertices. So it's like it's non-generic polytope from that way of defining it. Okay, so this is just an abstract.
Sorry, Taras, I'm a little bit lost with dimensions. So when you say that dimension of ZP is m plus n, it's real dimension.
Yeah. So yeah, the dimension so far as there is no complex geometry yet. All dimensions are real. Yeah, it's real dimension m plus n. Yes.
And it is described by a set of quadrics in CM. Yeah.
Yes, that's right. But those quadrics are not holomorphic. They're just
and they're not holomorphic. Yeah. That's what. Thank you.
They're not. So there is no way to define a complex structure from by embedding it somewhere. That will make do it differently. Yeah. Okay, so this is a moment angle manifold. It's defined. You start with a polytope and you write down an intersection of quadrics. And if P is a Delzant polytope, so it's like and the Delzant in particular rational, then this gives you back precisely the original construction, the level set for the moment map of the subtorus, giving us a kernel of this map. So now those things are rational. And therefore, this is actually a closed subgroup. But the point is that from this definition, it doesn't have to be rational over travel. If it happens to be rational with this extra Delzant condition, then it has a meaning in terms of symplectic quotients. All right, so now that's a more abstract definition, but it's still quite restricted. And we want to define it from a very purely topological way, and so that somehow will give us an idea on how to put some more geometric flesh on it. So let's call the moment angle complex rather than a moment angle polytope or moment angle manifold. So now instead of starting with a polytope, we start with an abstract simplicial complex. So an abstract simplicial complex is just a collection of subsets in a finite ordered set of indices, such that it's closed under passing to a smaller subset. So whenever you have a subset in your collection, which is called a simplex, and every smaller subset is also a simplex. That's a condition. So the abstract simplicial complex is just a special collection of subsets. So whenever you have a simplex, any subsimplex is also a simplex. And For technical reasons, we assume that empty set is in your collection. And now we look at the m-dimensional polydisk. In complex space, and we define what's called the moment angle complex. It's the same moment angle, but so far the definition is very different, but it's actually will be the same as I explained soon. So it's just write down the following subset in your complex polydisk. So for arbitrary I, a subset of M indices, you write down a subproduct in this polydisk. It consists of disks and circles, right? So whenever your index is in your set, then you put a disk on the appropriate space. And whenever your index is not in your subset, then you put a circle, a smaller subset. So it's this thing is in parentheses is always a product of disks and circles, which sits inside the polydisk. And then you take the union of all those products of disks and circles over all simplices in your simplicial complex. So you get some subset in your polydisk. And we denoted Z sub K. So the moment angle manifold was Z sub P, and this is Z sub K. So first of all, it has a natural action of the torus because all those subsets are invariant with respect to the torus action. And furthermore, it's some kind of exercise in combinatorial topology that whenever you start, when your K is nice, namely when it's a sphere triangulation, well, we think of it abstractly, but every abstract simplicial complex has a geometric realization as a polyhedron, as a union of simplices in a, say, Euclidean space, when in a fine space. So you just take those elements as a vertices and take arbitrary, say, in large m-dimensional space, you can take, say, the independent m-independent points and put the simplices on the subsets of the points, the convex simplices, and take the union of them. That's how you get a topological space, triangulated topological space from abstract simplicial complex. And if this space happens to be a sphere, so it's like a triangulated sphere, simplicial subdivision of a sphere, then what you get from this construction is a topological manifold. And this is the most general construction. It's called the moment angle manifold without any restriction, right? So it's this moment angle complex corresponding to a triangulated sphere. So rather than proving this, I'll give you kind of an example so you can get a feeling of what's going on here. So we start with an abstract simplicial complex, and out of this abstract simplicial complex, we'll build up a subcomplex in m-dimensional polydisk. So this M now is a complex dimension, like with CM. So okay, let's start with the boundary of a triangle. So I mean, we defined simplicial complex abstractly, but of course it's better to look at it geometrically, like with vertices and edges and triangles. Yeah. So this empty triangle that it has 3 vertices and 3 edges. So like if you speak of it abstractly, then it has 1, 2, 3. It's a simplicial complex on 3-element set. It has empty set. It has all 3 singletons, and it has also all 2-element subsets like 1, 2, 2, 3, and 1, 3. But 1, 2, 3 is not here. And then, so what you do is you take union over all simplices. So let's say 1, 2, 1, 2. You have disk on the first position, disk on the second position, and the circle on the third position. And you take the 3 subproducts like this, corresponding to all the edges. The things corresponding to vertices are already there, so you don't have to write them. So if you start with the boundary of a triangle, then you get the boundary of the disk, which is homeomorphic to a 5-dimensional sphere. So this is like a triangulated circle. So you get something homeomorphic to a manifold. Similarly, if you get the boundary of a square, then by writing something a bit more complicated, but still quite elementary, you get the product of 2 3-dimensional spheres. But now, if you start with the boundary of the pentagon, that's already quite a hard problem to decide what is it topologically. And the answer is that, well, you have to work rather hard to prove this, but if you do the same construction with the boundary of a pentagon, then you get connected sum of 5 products of S3 and S4. So it's 7-dimensional manifold because it's like triangulated circles, but it's already rather complicated. And similarly with arbitrary polygon, it's a connected sum like this, but even more complicated. So you see that it becomes quite complicated very fast. Even for the polygons, it's not easy to define what is it topologically. And well, the last example is something which is not a manifold, which you just with 3 disjoint points, just 3 one-element subsets, 1, 2, and 3. Then you get a moment angle complex like this, d times s times s, that corresponds to 1. So here disk on the first position and circles on the second, third position. Here disk on the second position and circles on the first and third position. So you have the union of those 3 things. It's something 4-dimensional. And again, well, that's easier than the previous one, but still you need to work. That's now an exercise in, well, not an exercise, problem in homotopy theory rather than in topology, in geometric topology. So that thing is homotopy equivalent to a wedge of circles. So it's also quite complicated, but nevertheless, this is not a manifold. So you see, so a manifold appears when you start with something triangulated sphere. And okay, so yeah, I haven't said this yet, but probably I should have, that this ZK is when you start with a polytope, like in these 3 examples, and you do the Hamiltonian symplectic Hamiltonian construction with these moment polytopes, then you get precisely this will be the moment angle manifold corresponding to the pentagon, for instance. So this is a combinatorial construction of the same object. So that tells you that the topology of the moment angle manifold, it's very much complicated. It's much more complicated than that Hamiltonian toric manifold themselves, or their symplectic quotients. Okay, so now, so this is somehow here, you have some kind of combinatorial topological construction involved here called the polyhedral product. I wrote it here. So it starts with as an input, it uses abstract simplicial complex and a pair of spaces. In this case, a pair of spaces is a disk and circle. So if you take a simplicial complex and you have a pair of spaces, you can build up what's called a polyhedral product. It's a subproduct in the m-fold product of the larger space. And it's a union of subproducts, and those subproducts are parametrized by simplices in your simplicial complex. So this is an example of this polyhedral product construction for the pair D, S1. You can use other pairs and you get some other even more familiar spaces. For instance, if you start with a pair C, C cross is just C without 0, then you take the similar kind of construction. You take the union over all simplices in your simplicial complexes of those subproducts. So you just, sometimes you have to throw away 0 from C. We call it's just some open submanifold in m-dimensional complex space. And it's also a toric variety in a sense that it has a action of a algebraic torus, C star torus. So this is algebraic one-dimensional torus. And just from the construction, it's clear that C star to the C cross to the power m acts on this U of k with an open dense orbit. So it's a toric variety. And for those familiar with toric variety, it's easy to understand what the corresponding fan is. So the toric varieties are parametrized by what's called fans, collections of polyhedral cones in a real space. And for this particular toric variety, the fan consists of coordinate cones. So if you look at the simplicial complex and you take just the positive spans of coordinate vectors corresponding to vertices in your simplices, so it's like the coordinate fan consisting of coordinate cones, then the corresponding toric variety is precisely this one, and those subproducts are this is just its affine cover. So those are affine toric varieties corresponding to single cones in your fan. All right, so, and then this toric variety is very well known in toric geometry. It's just slightly different way of looking at it as a polyhedral product, but the more familiar way is just as a complement of coordinate subspace arrangement. So toric varieties can be defined originally like by gluing affine pieces by the recipe given by a fan. That's a classical definition, or there is a quotient construction due to Battery of Cox and others, and also symplectic people, which rather than gluing things from pieces, it defines as a quotient of some universal space by an action of an algebraic torus. And this universal space is precisely this U of K. So it's usually defined as a complement. You have to throw away some coordinate planes from the complex m-dimensional space. And basically, if you do simplicial toric varieties or toric orbifold, then everything is determined. The combinatorics is determined by a simplicial complex, and you just throw away coordinate subspaces corresponding to non-simplices of K.
Taras, excuse me. When you pass to C star instead of S1, so you just from the beginning you might start with a complex torus, not real one.
Yeah, there'll be both complex and real torus. So when you work with this construction, then with this space, then it's actually has an algebraic torus section. Yeah. But the original one had only a compact torus section, and they'll be the two will be related.
I understand, but you see here you just pass from S1 to C star, and in the same way you may from the beginning pass from real torus to the complex.
Yeah. Well, you need to, we need to make some choices. Yeah. So for me, the torus is a compact torus, right? Because, well, I have my origin in topology, and yeah. So torus is a complex torus. Whenever I mean a C star torus, I say a C star torus, or I say algebraic torus. Yeah. So, and toric variety it has not just a compact torus section, it has an algebraic action of an algebraic torus. So in this case, yeah, it is actually C star torus acting. So yeah, well, I need to, that's a feature of the story that you need to pass between compact and algebraic torus constantly, yes. Okay, so well, you have a theorem. Well, that's the first part is just another kind of exercise to see that this way of writing down a thing, the space as a union of products of C and C star is the same as taking out some coordinate planes. But what is more important here that so now you have ZK, the moment angle complex, which is defined as precisely the same way, but with C replaced by D and C star replaced by S1, the circle. And obviously, ZK sits inside U of K because disk sits in C and circle sits in C star, but it's actually deformation retraction. So the two things have the same homotopy type. And this is true. This is just a combinatorial topological result. It has nothing to do with toric geometry. Also, in toric geometry, this has some meaning, but the toric geometry is a rather restricted case when you have fans and so on. But here, it's just purely topological statement. But there is an equivariant deformation retraction. I'm not going to prove.
Is it a deep theorem or it looks so?
Well, not really deep, yeah. But I mean, but you need to work. It's not straightforward. Well, you can try to think in the following way that, well, okay, that C deformation retracts onto D, right? And of course, C star deformation retracts onto S1, right? But the problem is that you cannot do it simultaneously. You cannot deformation retract C onto D such that the C star retracts onto the circle, right? So it's this construction is like it has obvious functorial property and it's homotopy invariant, but you cannot use this in this straightforward way. So you have to do something a bit more clever, but it's not really deep. Yeah, it's just some inductive procedure by adding simplices one by one and constructing this deformation retraction by induction. Okay, so but what's important for us is that this ZK is somehow the compact part of this universal toric variety, right? So, well, I'll illustrate it on a very simple example. So when you have this boundary of a triangle, then this universal toric space is just, you have to throw away coordinate planes corresponding to non-simplexes. But in this case, there is only one non-simplex, 1, 2, 3. The whole thing is not a simplex, so you have to throw away Z1 equals to Z2 equals to Z3 equal 0. So that's what your U of k is, just C3 without 0. And it's, of course, deformation retracts onto a 5-dimensional sphere, which is the moment angle complex. Okay, so, right. So now we come to the main part. So this deformation retraction, so this U of k is a very nice holomorphic algebraic variety. It's not affine, but it's like quasi-affine. It's a complement in an affine space to some affine, very simple affine variety. And it has a holomorphic, it has an algebraic torus action. So in particular, there's a compact torus acts on it by holomorphic transformations. So if you can realize this retraction by geometrically as a quotient by some holomorphic action, then it will give you a complex analytic structure on that moment angle manifold. And that's how it works. So this deformation retraction can be realized as an orbit quotient map for a holomorphic free and proper action of a complex analytic subgroup inside the algebraic torus. So this is just the complement in CM to some coordinate planes. And this is, well, a space or a manifold which can be defined in several different ways. It has a torus section, a compact torus section. So if you can realize this deformation retraction as an action of an analytic subgroup, then you'll put a complex structure onto this quotient. But the problem is that this thing is non-compact, and the action is also, the group will also be non-compact, and therefore you have like holomorphic or even smooth action of a non-compact group on a non-compact space. And even if the section is free, the quotient may fail to be a manifold because you need to check the Hausdorffness as a separatedness condition. And with non-compact groups, this is not automatic. So that's an extra condition on the action. It's called like properness. So, but if you have a proper free action, then the quotient is a manifold. And if you have a holomorphic proper free action, then the quotient is a complex manifold. It has a complex structure. And you cannot always, you cannot hope for that this works in general. So deformation retraction exists for arbitrary k, but you can make it holomorphic only under some extra conditions. And these conditions are precisely the same as in toric geometry. You need some fan structure. You need that you not just start with an arbitrary sphere triangulation, but you need to start with something related to a fan. So in convex geometry, it's called like star-shaped triangulation. It's weaker than being convex, but it's still a condition on a triangulation. So like star-shaped triangulation is a simplicial complex, is a triangulation which you get by taking a complete simplicial fan and intersecting it with a unit sphere. So if you have a complete simplicial fan, like a union of simplicial cones which covers the whole space, and the intersection of any two cones is a face of each, like you have a complete simplicial fan and you intersect it with a circle, then you get a triangulated sphere. And you may start with a polytope, with a convex polytope, simplicial convex polytope, and that also gives you a triangulated sphere. The boundary of a simplicial convex polytope is a triangulated sphere, and it's star-shaped, but it's stronger. So like the simplicial fans, the triangulation corresponding to complete simplicial fans, they sit strictly between convex triangulation, simplicial polytopes, and arbitrary triangulations. Study not every triangulated sphere can be obtained as a simplicial complex underlying a complete simplicial fan. And also not every complete simplicial fan is combinatorially equivalent to the boundary of a polyton. Okay, so and this fan condition, complete simplicial fan condition, is something which translates into the properness condition of the appropriate action. And again, this is somehow this is also known in toric geometry, but then it is proved in a algebraic way, like using that. I mean that when you try to build up toric variety by gluing affine pieces, you need the fan condition for the result to be Hausdorff or like separated in algebraic language. So that separatedness condition, which is equivalent to just it's being Hausdorff in ordinary topology, is in fact equivalent to the condition that the cones corresponding to affine pieces in a toric variety do not overlap, and they intersect as a facet. So that's somehow kind of a miracle. So that's one separatedness condition from toric geometry, like the fan condition. The fan means that just a cone, you have a collection of cones and they form a fan whenever they can be separated by hyperplanes, pairwise separated by hyperplanes. That's one separated condition. And another one is just you either build up a toric variety or you do this topological business with moment angle manifold, take the quotient, and that the action is Hausdorff. That's another separatedness condition. And the two are actually equivalent. So that's how it works. So, okay, so now.
So sorry, can I ask a question about the previous slide?
Sure.
So what is a sphere triangulation which is not such that the underlying complex is not a complete simplicial fan? I'm kind of
how to construct such an example? Or...
Yeah, I'm struggling to imagine how that would.
Yeah, that's not easy. Well, okay, well, so I mean, first of all, I mean, there are two conditions right here. So I mean, if you have so first of all, you can construct a complete simplicial non-singular fan in three-dimensional space already, such that you cannot put vertices. Which
is not normal. So
yeah, not normal yet, but that's not.
I'm just asking about the difference in definition. The difference is that what is the difference between the two notions? So when is a sphere triangulation not? What is the difference in definitions?
Yeah, so if you take a fan which is not normal, right? These examples are well known in toric geometry, so
sure.
Order. Then, but nevertheless, if you start with a standard one, the three-dimensional, if you look at if you look at it combinatorially, then the corresponding simplicial complex is, although it's not realized in a convex way, but it's combinatorially equivalent to a convex triangulation. So it's not a counterexample to what I'm talking about here, right? But you can produce counterexamples nevertheless. So to do this, you need first of all to construct a non-convex triangulation, right? So in starting from dimension 4, or I mean three-dimensional triangle, there are three-dimensional triangulated spheres which are not combinatorially equivalent to the boundary of a simplicial polyton. In dimension 2, such things do not exist. There are just this
okay. Okay, yeah, I get it now.
And then, but this is still not quite the thing you need. Then you need to work. You need to glue these things together, and then you can prove that the resulting combinatorial sphere triangulation is actually cannot appear as an underlying triangulation of a complete simplicial. So these things exist starting from dimension 3, the dimension of the sphere, or the fan is 4-dimensional.
Okay, but like sort of trivia, if the triangulation is star-shaped, a star-shaped triangulation is trivially the same thing as a complete simplicial fan.
That's right. Yes.
Okay.
Yes.
Thanks.
Yes. Yeah, I gave a definition of the star-shaped convex geometry here, and it's obviously equivalent to it being underlying complex of a complete simplicial.
Okay. Thanks.
Yeah. So now, okay, let's see how it works under how to. So now let's try to. Oh yeah, I'm sorry. What time? So okay, it's I know. Shall we make a break here, or I don't know? Maybe
No, usually we don't have a break.
you don't. Okay. Then.
But if you need, we can.
No. I don't need it. Let me just take a watch so I have much time. All right, so now let's realize this plan. Let's, instead of, I haven't actually defined this deformation retraction, but let's now define it in a geometric way as a quotient by an action of a complex analytic subgroup. So to do this, you just take, so assume that you have this situation when your K is an underlying complex of a complete simplicial fan. So remember, note that I never mentioned rational here. So the rationality condition doesn't come, it's not part of the construction.
You mean rationality for the coefficient, so it's not.
So the fan, yeah. So that those the fan, there is no lattice here. Just the fan is in Rn. Yeah. The generating vectors of the one-dimensional cone need not be rational. So you take those generators; they're just vectors in Rn. You pick up some generators. I mean, if you have a lattice, then you have a canonical choice, that's the primitive generators. But here you just pick up some arbitrary generators, real generators of one-dimensional cones. And using this, so that's also be a part of data, defining the complex structure eventually, the choice of those generators. So if you have a generator, so you have a complete simplicial fan in n-dimensional space, and you have m of them. So and from this generators, you can define a map, just sending the basis vector to the generator. And that's a surjective map. And you can then like take the kernel and exponentiate it. So you did take the kernel of this map, that will be just m minus n dimensional subset, and you take coordinate-wise exponentials. Or you can write it down in multiplicative notation like this. So that will be a subgroup, m minus n dimensional subgroup in the multiplicative group of m tuples of positive reals. And for those of you who are familiar with toric geometry, this is very similar to the algebraic subgroup, which is defined in the Cox construction. But this is a real subgroup, and it has real dimension m minus n rather than complex dimension m minus n. So this is a real subgroup so far. Nevertheless, it acts on this toric space, a complement subspace arrangement complement by coordinate-wise multiplications. And from the first theorem, this is just the real result underlying the complex analytic construction. So if you start with a complete simplicial fan with m one-dimensional cones and with underlying simplicial complex K, not necessarily rational fan, just arbitrary complete simplicial fan, then this group that you define from this fan by choosing a generator, for every choice of generators, actually, it acts freely. The freely is easy. It's just coming from the fan condition, from the simplicial fan, that the generators of the cones are linearly independent. And properly is that's much harder. That properness is basically equivalent to the fact that you started that so like how the fan condition comes here. What is a fan, right? The fan is it's determined by two pieces of data. One is combinatorial, this underlying simplicial complex K, right? And then you need to specify generators of one-dimensional cones. Once you know the simplicial complex and the generators of one-dimensional cone, you know everything. You take for every simplex, you span a cone by the vectors corresponding to this simplex, and take the union of those cones. But of course, the fan condition is something extra. So if you just pick up arbitrary generators and arbitrary simplicial complex, then you get just a bunch of cones. It may or may not form a fan. The cones in your collection may or may not have being like separated by hyperplanes or intersected faces. So like if you start with K and those generators, that's already like define your collection of cones, which may or may not be a fan. And they also define you the subgroup. So this subgroup is defined just using the generators, but the space on which the subgroup acts is defined using the combinatorial piece of data, the simplicial complex. So the R action on U of K is defined by the collection of cones. And it's proper if and only if this collection of cones form a fan. And once it acts freely and properly, you can deduce that the quotient is a smooth manifold using the transverse atlas. And furthermore, it's equivalently, it obviously has a TM action, and it's equivalently homeomorphic to the moment angle manifold, to the moment angle complex, sorry, corresponding to the fan. From that case, just a combinatorial definition from disks and circles. So this is how you can smooth it first. So in general, it's even like, yeah, even if you look at those examples which I gave you with disks and circles, right? It wasn't clear from that construction that it's actually smooth. So you have like, sorry, if I go back slightly, like here. So for instance, here we have a 5-dimensional sphere, but it has, if you write it down like this, it has like angles. It's not smooth. It's homeomorphic to a 5-dimensional sphere, but this gadget is not smooth. So, well, of course, here you can smooth the angle, but in general, it's not at all clear how to do that in a consistent way. And that's give you, so that's even not clear in general whether this moment angle manifold has always a smooth structure, but in this particular case, it has, because it can be smooth. When your K is a star-shaped, then it can be smoothed with this procedure. Well, of course, if you started with a polytope, that's even stronger than being a fan, right? Then you can smooth it using the very first thing I mentioned, the intersection of quadrics. The intersection of quadrics is smooth, and that's another way to smooth them, different from this one. But it works in a more restricted case when you have a polytope rather than a fan. That's strong. That's more restricted case. Okay, so like freeness is corresponding to being simplicial, and properness corresponds to being a fan. Well, yeah, I haven't defined what the proper action is, so that the action map is proper. So you have like, yeah, well, yeah.
What do you mean by saying that the smoothing of the polytope Z of K by looking on it as intersection of quadrics?
Well, I haven't proved that. I just mentioned that, yeah, that when you define this moment angle complex as a gadget construct from disks and circles, this one, and if you take K to be the boundary of the dual polytope, of the moment polytope, then this is homeomorphic to the moment angle manifold defined as an intersection of quadrics. That's not really hard to check. Just this is just another way of defining the moment angle manifold. But in this way, it's not defined as a smooth thing. It's only homeomorphic to the intersection of quadrics. So that's actually was the thing how we first looked at that, and then later we encountered the other like definitions like from intersection of quadrics and eventually from this quotient, right? So that for us, the moment angle complex is this gadget, and therefore by writing it down as an intersection of quadrics, you put a smooth structure onto it. That's one way to do, okay. And another way to do is take the quotient by a proper action of a contractible subgroup. Yeah. So yeah, of course, yeah. I mean, if you define ZK as ZP as an intersection of quadric as a level set for the moment map, then it's already smooth, and it can be proved that those two smooth structures are equivalent.
Okay.
But this is more general situation when you don't have a polytopic triangulation, and that like in terms of projective toric variety, that corresponds to a non-projective situation. And in fact, asymptotically, toric varieties are not projective. If you pick up an arbitrary fan, then it's just randomly, then it almost never a normal fan, right? So also most examples we know are projective, of course, but I mean, if you look at it like as a subset, and from that like that asymptotic behavior, there are theorems like that it's never projective, never normal fan. So it's really, that's a much larger family. All right, so now that this is just a real result, but now from here it's quite easy to guess how to make it holomorphic. You just put a complex structure on this group. For this, it has, of course, yet that you need that m minus n is even, but that's just a technical assumption which can be achieved quite easily by remember, m is a number of one-dimensional cones and n is a dimension, right? So in a sense, you can play with like what's called empty cones. You can add up arbitrarily many vectors which do not, like ghost cones. They do not correspond to one-dimensional cones. Or if you think in terms of polytopes, you can write down a polytope, say, like as an intersection of m half planes, half spaces, but you can add, or you can always add one redundant half space which does not affect the polytope, like some half space far away from your polytope, and that gives you some extra equation. So like that polytope is the same n-dimensional, but you have one extra equation, which is redundant. And in this way, you can increase m by 1 to make this difference even. And in terms of the manifold, that procedure corresponds to multiplying the moment angle manifold with a circle. Or in terms of toric variety, it corresponds to multiplying this universal toric space U of k by C star. So you can always make this thing even by just playing with this ghost or redundant vertices or redundant cones, redundant half spaces. So assuming m minus n is even, so m is a number of generators, n is a dimension of your fan. Then you can basically consider, and let L be a complex dimension of your holomorphic group. So you choose a linear map from CL to CM satisfying the two conditions. So the first condition is that when you compose it with a projection onto the real space, taking the real part, it becomes a monomorphism. And the second condition is actually when you compose it with this map sends the basis vector to the generator of a cone. That's Q map. It's just a standard map coming from a choice of generators for your fan. Then it's 0. So that's just a fancy way of saying that put a complex structure on this. So you just take the kernel of this Q and map a complex space onto it of the same dimension. So just in this way, you put a complex structure on this kernel, on this m minus n dimensional real space. But it's convenient to write it this way because then it can be like defined as a data which defines your complex structure. So you have this diagram like this. So you have this map. So now the dimensions are complex. This complex dimensions, and these are real dimensions. And now you exponentiate it to get a holomorphic subgroup in the algebraic torus. So as a result, you get a closed subgroup in the algebraic torus, but it's only a holomorphic subgroup. It's not an algebraic subgroup. You embed holomorphically CL into C star to the power n. And because it's a holomorphic subgroup in this algebraic torus, it acts on this complement of coordinate planes by holomorphic transformations. All right, so what are the choices here? And now you can, okay, well, I'll state the results later. Let's probably first briefly go through some basic examples of how it works. So for instance, if you start with a empty simplicial complex, so that's like it has two ghost vertices, right? It's a simplicial complex on two elements, but it has only empty set. It doesn't have it doesn't have any vertices. It just has empty set, and that's it. So the parameters here, the dimension is 0. The number of vertices is 2. So m minus n is 2, and L is L is just the half of it, so it's 1. And obviously, this Q, and this is Q maps from R2 to R0. This is a 0 map. So this condition is void, but this condition is non-trivial still. A. So you need to, so L is 1, so you need to map C into C2. So you can always write it like this, some parameter alpha, and then your subgroup is just that consists of those exponents. And if you think about this first condition, that the composite with the real part is a monomorphism, then you see that it's equivalent to the condition that alpha is not a real number. And under this condition, you actually get an embedding. If it has some real part, then it glues some points in C. But if A is not real, then it embeds C into C star square. And the quotient, well, is just one-dimensional complex manifold. It can be nothing but just a elliptic curve or a one-dimensional complex torus. And well, you can think of it by taking quotient of C star square by this H. You can take out one coordinate, and then on the other coordinate, there will be some identification. And if you look at it a bit closer, then you will see that that's precisely the quotient of C by the lattice with parameter alpha. That's this condition features here. So that's just a different way of writing down the standard one-dimensional complex torus. Instead of writing it as a quotient of C by a lattice, you write it as a quotient of C star square by C. And you can do the same business with arbitrary holomorphic torus. So we started with empty simplicial complex on 2L elements. And by varying this map from CL to C2L, you can get any complex torus with this quotient. So now again, a complex torus you get, instead of writing as the quotient of CL by a lattice, full dimensional lattice, a full rank, you write it as a quotient of C star to the power 2L by C to the power L. So this complex torus is a moment angle manifold corresponding to empty simplicial complex, and it has a complex structure as this quotient. Okay, so now we have this result in the complex analytic setting with my former student Yuri Ustinovsky. So if you start, that's just the same as the previous one with in a holomorphic setting. So you have a complete simplicial fan with m one-dimensional cones. And now you need to assume that m minus n is an even number. Then you have this holomorphic action of this closed subgroup in the C star torus, and it's free and proper, and therefore the quotient is a complex manifold of this dimension. The real dimension is m plus n. The complex dimension is m minus l. And then you have this TM equivariant diffeomorphism with a moment angle manifold, which gives you a complex structure in which the torus acts by holomorphic transformations. It actually also has a C star torus action, C star M action, but it's not effective. It has an ineffectivity kernel. But the compact torus action is effective. So in this way, you make this moment angle manifolds into a complex manifold as a quotient by a holomorphic action of a compact subgroup.
Excuse me, I'm just, so this is pretty much the same theorem as what's the difference between this theorem and the previous theorem where
I mean, there is a more, like this complex structure depends on extra parameters. It depends on this choice of this map, right? So you need to put a complex structure. That is not, I mean, the proof is just, I mean, actually the result is topological, so it's just that this properness is a key thing here. But then you just say that by putting a complex structure on top.
Oh, okay, I see. So, so this is complex analytic version of the same theorem. Okay.
So it's just, it also in a way describes you this, the set of data you need to define a complex structure. It not just says a complex structure, it exists, it somehow describes it in terms of some data. And as I show in the next slide, it's actually all possible complex structures can be obtained by this. All possible invariant complex structure on those moment angle manifolds can be obtained by this construction. Okay, so so this is a holomorphic result, and now so as I said, that's whenever you have if you happen to have a holomorphic a complex analytic structure on this manifold in which TM acts by holomorphic transformation, then there is an theorem in the opposite dimension, the Converse Theorem, which tells you that this complex structure can be obtained by this procedure. Namely, if you have a complex analytic structure, then you need to, because
Maxim, excuse me, Taras, sorry. You have a lot of choices to make, but are all these complex structures equivalent in some sense, or they're distinct?
No, they're certainly distinct, but I mean, we cannot say that they're all, I mean, there are certainly deformations. So I mean, most of them are distinct. There may be some gluing, but we cannot, at the moment, that's one of the big problems to define the moduli space of this complex structure on those manifolds, but at the moment we have very, very small information about this. But in general, the dimension is right? So I mean that the number of parameters is the same as the dimension of the modular space. So there might be some gluing, so some data may still give the same structure, but if you just perturb them slightly, then you get a different structure.
But how you count the dimension of complex structures on this manifold?
Well, you can
is there
deformation space, that you can identify some. I'll tell you some Co Homology you can calculate, some basic.
Okay.
I'm not sure I'll get to this because I have just slightly more than 10 minutes left, but I'll maybe briefly. So, so how to go the other opposite way? As I said, you can, first of all, you can extend once you have everything is compact here. So just if you have that's some, you need to check that you can extend the torus action to a whole. If the compact torus acts by holomorphic transformations on a compact manifold, then you can extend it to a holomorphic action of the algebraic torus. But this holomorphic action is that need not to be effective. So it has global stabilizers. It has global stabilizers, and these global stabilizers are precisely this subgroup H, which is defined before. So if you happen to have a TM invariant complex structure, then you extend it to the holomorphic action, you define the global stabilizers, Then you write down the Lie algebra of this holomorphic subgroup, and that the Lie algebra is precisely this complex space that you started from. And how the fan comes from? Well, you need to look at the quotient by the real part of this Lie algebra. And here you have the standard fan, the fan for this U of k, that consisting of coordinate cons. And that's exactly why this is like an if and only if statement. That's like that the geometry of this complex structure tells you that this fan is mapped onto a complete simplicial fan in the complex space. That's how you recover the fan. And that's a theorem by Isida, our colleague and co-author from Japan, that actually that's the opposite theorem, that every complex analytic structure can be that complex manifold. Well, I formulated it slightly vaguely, but I mean that like if you have a complex structure which is invariant under the TM action, then it's TM equivalently biholomorphic to the quotient of this form. So you cannot get any other complex structures, and in particular that means that somehow you can have moment angle manifold, and it can be a smooth manifold, but it doesn't admit any complex structure if K is not an underlying complex of a complete simplicial fan. Well, it doesn't admit a complex structure invariant by the torus. Just a second. Yeah, my son did something bad. I'm sorry. Just. All right. So yeah, now, as I said in the beginning, that this family of complex manifold includes almost all known examples of non-Kähler. Well, that's quite a strong statement. Well, the classical examples of non-Kähler complex manifold. In particular, the very first example of a non-Kähler complex analytic manifold was a Hopf surface. And it can also be defined, arbitrary Hopf manifold actually can be defined as a complex moment angle manifold for a particular fan. Namely, for the fan, like for the fan corresponding to the, in the language of toric variety, for the fan corresponding to the complex projective plane, projective space. So if you take the complete fan with cons generated by all proper subset of those vectors, like the basis vectors and minus some of the basis vector, and look at all the proper subsets. So in dimension 2, you get like 3 cons. And then, well, okay, I'll go through this briefly. So you need to add one empty con to make the difference even. So then you can define this map. And then you also have this universal, the moment angle manifold here. The boundary of the simplex, this is the underlying complex for this fan, it gives you a sphere, and adding one ghost vertex multiplies it with a circle. So you get a product of a circle and an odd dimensional sphere. And the universal space is a product of C star with Cn plus 1 without 0. And then you take quite a similar thing as in the previous example with tori. You define a one-dimensional subgroup with one complex parameter alpha, which is not a real number. Its imaginary part is not non-zero. And then you take the quotient of this space by the action of C given by this holomorphic subgroup. Write it like this, and then again you can take out this C first, and then on this example you'll have some identification, and these identifications are precisely the diagonalizable operator with eigenvalues like exponent of 2 pi I alpha. So this is just a diagonal matrix, and this alpha is not real, so the module of this eigenvalue is not 1. But the classical Hopf surface corresponds to like the case n equals 1. So it's a quotient of C2 without 0 by like W is identified with 2W. So when this thing is 2, so that's a Hopf surface. It's homeomorphic to S1 times S3, and it has a complex structure, which is neither Kähler nor symplectic because it doesn't even have second dimensional cohomology. So in general, you can, from this procedure, you can get arbitrary Hopf manifold. Well, I mean arbitrary Hopf manifold corresponding to the action of a diagonalizable operator with eigenvalues of absolute value more than 1. You can put arbitrary eigenvalues here, not just the same ones, the scalar matrix, so that you can get all the Hopf manifolds like this. And yeah, so now you can, what can you do with those manifolds? Why you should be interested in looking at that? Well, first of all, they're very closely, intimately related to toric varieties. And let me, probably I have only time to explain about this relation, and I won't have time to talk about Topological homology much. But anyway, so like on every complex manifold with a torus section, you can have kind of holomorphic foliation, which is defined in this particular case as follows. So you have this. So you define your manifold as a quotient of this U of k by the action of the holomorphic group H, and you can look at the, so that H is a complex Lie algebra, and you look at its real part, and its real part is a sub-algebra in the Lie algebra of the complex compact torus. So you can look at the, you can now exponentiate it back and get a subgroup inside Tm. But this subgroup is not necessarily closed. It may be like a dense, it may be a dense subgroup, or it may be just non-closed. Its closure may be a subtorus of a positive codimension. So it's just some subgroup, subgroup in a torus, not necessarily closed. And like in the toric situation, in the symplectic situation, it's easy to check that the action of k on, if you look at the restricted action of this k, then it's almost free. And in this way, you get a holomorphic foliation, so by the orbits of this almost free action. It's a very special foliation, of course. It's actually an almost free action. And if this subspace happens to be rational, then K is a subtorus.
Taras, orbits are closed of this foliation, of this action, or no?
No, not necessarily. No. That's a major problem. Yeah, I mean you cannot just define the leaf space because it'll be some non-Hausdorff space. So the orbits in general are very far from being closed. Yeah. But if K itself is a subtorus, then the orbits, of course, are closed, and you have an almost free action of a subtorus. And this quotient by this almost free action is precisely the toric variety. Or it may be an orbifold if the action is not free, but nevertheless, it's just a very nice toric variety corresponding to your rational, in this case, rational complete simplicial frame. And this toric variety, it can be defined either from the symplectic construction, as I said in the very beginning, as a quotient of the moment angle manifold by the compact torus, or by an algebraic construction by taking quotient of this open toric variety, the standard one, the universal one, by the complexification of K by the algebraic torus. In general, it's a quasi-torus, but that's, yeah, I'll skip this subtlety here. So if in the rational situation, if your data kind of defining the complex structure is rational, then you still get some complex manifold, but it's also related to toric varieties. And in this case, this holomorphic foliation by the orbits of the section becomes a fibration, or rather Seifert fibration, because the quotient is an orbifold, but the quotient is a manifold, and it's just a holomorphic fibration. And the fibers are precisely those complex torus that we defined in the very first examples. So that if you take the complexification of this subgroup by H, it has precisely the half dimension, and this is just a complex torus, which I described before. So let's look at this as a following. That's precisely the relation to the toric world. So we have this in the rational case. In the rational case, we have always this universal space which sits inside Cm. And then you can take the quotient construction of the toric varieties. That's a vertical arrow. It's a quotient of by the action of the algebraic torus of dimension m minus n. But now you can factorize this quotient construction into two arrows. The first one is our quotient. That's a moment angle manifold, and this is a quotient by CL, by holomorphic action of CL. And then you can take quotient further down by taking KC modulo H. That's a torus. So this is a holomorphic foliation of holomorphic fibration. So moment angle manifold is a total space of a holomorphic vibration of the toric variety with fiber a compact complex torus. That's in the rational case. But in the non-rational case, you only have this arrow. And instead of that, so like this tori, they open. They're no longer closed. They become non-closed subgroups, and you have a holomorphic foliation by a non-compact group. And well, that's holomorphic foliated manifold. This can be thought of as a model for what's now called the non-commutative or non-rational toric varieties. There are several groups of people studying, currently exploring this. I'll mention just two of them, Katsarkov, Lupercio, Mersman, and Perhovsky, and Rachu Zoom. So like the non-rational deformation of a toric variety is just a foliated moment angle manifold. And this raises several questions. One of them is like, yeah, I probably, if I can take a couple of minutes, I'll just go briefly through that. So one of the question, of course, is understand the modulus space. And to do this, you need, well, that's only one aspect, but you want to understand some invariants of those complex structure. And the most basic ones are the Dolbeau homology and the Hodge numbers. And you can do this to some extent. And you get some nice answers, which are very much related to what's known in the toric world. So first, there are topological results, which we started from like 20 years ago with Victor Buchstaber. So like from a simplicial complex, you can write down this, what's called the Stanley-Reisner ring. It's a quotient of the polynomial ring by a square free monomial ideal corresponding to non-simplices of K. We take out the monomial corresponding to non-simplices, and this ring is precisely the equivalent cohomology of either U of K or ZK, that TM equivalent deformation retraction between them. So it's the same equivalent cohomology. This is the equivalent cohomology. And this is also the equivalent cohomology of the toric variety, the simplicial toric variety. And yeah, the toric variety is scalar, or equivalently projective. For toric varieties, the two things are equivalent. Symplectic, projective, and scalar are all equivalent for toric varieties, toric manifolds. And don't leave with the fan is the normal fan. And but whether it's projective or not, you can calculate the Dolbeau homology. That's a old result of Danilov from 70s. That actually the Dolbeau homology for toric variety, toric manifold, smooth toric variety, is generated by, so it's like the Hodge rhombus is just one line, so everything sits on the diagonal, and it's generated by classes of by degree 1, 1. And you can write it down as a quotient of the polynomial ring by two ideals. The one is the Stanley-Reisner ideals generated by monomials, and another one is generated by certain linear forms. This is the Dolbeau homology of the toric variety. And yeah, you can write down the Hodge numbers as they're defined just combinatorially. And we also have this result with Victor Buchstaber about the cohomology of the moment angle manifold. That's slightly more complicated. So you need to like resolve that face ring as a modulo as a polynomial ring and calculate the algebraic homology of this cohomology as a Tor module. This is like quite well known in combinatorial commutative algebra, how to calculate this. There are several descriptions, including the combinatorial one. And then the first result with Ustinovsky was a calculation. Well, I shouldn't call this a calculation, a model for the Dolbeault homology of the historic variety of this moment angle manifold. So that from this you can say something about the modular space of the complex structure, for instance, by calculating H10. So you can have a description of this Dolbeault homology, which in a way is similar to the description of the de Rham homology, which we had with Victor a long time ago. So it's similar Kosul type model. So it's like you take the differential graded algebra with a simply defined differential and take its homology.
I'm sorry, may I ask a question about this previous slide?
Yes.
So what is H tilde?
That's just reduced simplicial cohomology. So you can calculate those Tor modules as the sums of just simplicial cohomology of full subcomplexes. You restrict your K onto subsets of vertices, right? So, and that you take all possible subcomplexes, the full subcomplex, and calculate their simplicial cohomology and sum up. And with a shift, you get the cohomology of that K. And you can put a multiplication onto this sum so that it becomes a ring isomorphism.
But it's not clear, right? How to multiply.
Well, that's well, I mean, so this isomorphism is multiplicative. So we just the multiplication is like this. You take the only non-trivial products are coming from non-intersecting full subcomplexes. So when Ki and Kj are not intersecting, there is a possibility for a non-trivial product. If they overlap, then the product is 0. And if they do not overlap, then there is a map from like Ki of this cohomology tensored with the cohomology of Kj to the cohomology of K sub I union J. And that's precisely the ring structure. So that's about this product structure, but nevertheless, it's quite complicated. All possible non-trivial topological phenomena can occur here. Well, it seems that, can you hear me? I think
Yes,
my
yes.
internet connection was lost for a moment.
No, it's okay.
It's okay, all right.
At least on my side, there was no interruption.
All right. Yeah, maybe just Zhenya, who was frozen for a moment. Okay, so yeah, and as a corollary of this, we can say that two collapse results for the spectral sequences related to the Dolbeault homology. The one is like the analog of the Leresser spectral sequence for this holomorphic foliation, or for holomorphic vibration. So it collapses at the E3 term, the Borel spectral sequence for this. It converts to the Dolbeault homology of that case. So we know the base, that's the Danilov's result, and we know the fiber, of course, that's just this exterior algebra. So that's just the E2 term of the spectral sequence. And once it's the same as a whole Dolbeault homology, we can say that it collapses. And secondly, that there is a Fröhlicher spectral. For the in the non-Keller world, the Dolbeault homology is much larger than the de Rham homology, because the Dolbeault cycle is not necessarily a de Rham cycle, and therefore there are usually much more Dolbeault homology, and there is a spectral sequence relating the two called the Fröhlicher spectral sequence. And in this case, it collapses in the E2 page. So in the rational case, there are lots of ways to say something about the Dolbeault homology, but we do not have a generalization of this result to the non-rational settings because we do not have a vibration to apply those spectral sequences to. And then the only thing we can say about, in general, in the non-rational case, is a basic cohomology. That's probably the last result which I'll show you. There's also a part about transverse Keller forms. Yeah, I'll only briefly, that's our work with Misha Verbitsky and Yuri Ustinovsky. And as a corollary, I just mentioned that under generic assumptions, those, as I said, those manifolds, those complex structure were very far from projective algebraic. In particular, they in general, if you pick up a generic complex structure, then there are no non-contact constant meromorphic function of this manifold. And in particular, the algebraic dimension of this manifold is 0. So no meromorphic function, no divisors, no even only finitely many submanifolds, only finitely many complex analytic submanifolds. So it's very far from being Keller or projective. So like, of course, there is another example of this phenomenon, like if you take an arbitrary complex analytic torus, it is Keller, but still it doesn't have proper submanifolds except for points, complex submanifolds. But in this way, they behave in the same way, but furthermore, they are not Keller also. Well, actually, they are not Keller from a purely topological reason, because they are almost too connected. Like in the case with, they're always like something like two connected manifold times a torus. So that two-dimensional cohomology is not large enough to support a Keller form. Like in the Hopf example, for instance, there is no second cohomology. In general, there might be second cohomology, but it's too small. So it's the proper power of this Keller, hypothetical Keller form cannot hit the fundamental class. So the only case when it's Keller is a torus. The torus is Keller, but if it's not a torus, then it's not Keller. Yeah, so the last thing I mentioned is this basic cohomology. For this foliated manifolds, you can have this basic complex, which like turns into the cohomology of the base space when your foliation turns into fibration. If you have a holomorphic fibration, then the basic cohomology becomes the cohomology of the base space, the quotient. But in general, you have this basic form, and this basic cohomology is like an approximation to the cohomology of the leaf space, which is in general, it's very, very bad and non-Hausdorff. In this case, we can say this result, which settles some kind of problems, which people asked for about maybe several years ago, like that how the basic cohomology of those complex analytic moment angle manifolds or other classes like LVM manifolds look like, and it's actually the answer is the same as in the toric case. So the basic cohomology has the same structure as a ordinary cohomology of the toric variety. This with the quotient by the two ideals, and it's the same, but now it's just the basic cohomology instead of the cohomology of the toric variety. Yeah, it settles some conjecture, and yeah. If it's a compact torus, then the basic cohomology becomes the cohomology of the toric variety. Yeah, the proof is using the Cartan model and some formality results. So it's like also topological. So yeah, sorry, I think I need to stop here. So yeah, here are some references. Some of them are published, some of them are not yet. So yeah, if there are any questions, I'm happy to answer. Thank you for your attention.
Thank you.
Okay, I have not just a question, but probably absolutely vague association with something I knew from the integrable theory part when you're studying, okay, from algebraic point of view, you have a space fibered by tora which have dimension bigger than the base, not like in the integrable, completely integrable case, and you cannot make the Hamiltonian reduction because the kernel of some symplectic form goes along this tora, and that's why it can be everywhere dense. It seems like it looks very like to this setting you considered.
Yes, in a sense. Well,
then probably Taras, we should talk later more, because I can provide you with some examples of the situation you are looking for.
Yes, please.
From reasonable integrable systems.
Yes, I'll be very much interested. We haven't looked at the precise relationship of this particular study with the integral systems, but we have looked at some something related to those. There is some aspect, other aspect
no,
of this,
they
like with
all,
finding like Lagrangian submanifolds in toric varieties, and there you are precisely can look at some special integrable systems related to that. But this is, as you say, this system is not like integrable because the dimension of the torus is very big. Yeah, and
yeah.
what you can hope for is precisely this. What probably what you said is what you said is somehow related to what I skipped about this transverse scalar form. So that those complex analytic manifolds, they have like forms which are not scalar, but they have kernels precisely along the fibers, which are the tori.
No.
And probably it has some meaning in terms of that integrable system, not integral systems that you mentioned. But yeah, if you
no, they're integrable in algebraic sense because you can solve the equation just writing them in terms of theta functions.
yeah, sorry, I meant not Hamiltonian, non-Hamiltonian. Yeah.
But you cannot make them Hamiltonian.
Yes. That's what I meant. Yes, sorry.
Okay. Okay.
Yeah. So I'll
let's stop.
Okay, yeah, sure. If you can let me know of some literature we can look at for this relationship. So you say that people studying integrable system have looked at those like fibrations with fiber, holomorphic fibrations with fiber high dimensional tori. Yeah, so that's
yes, it's a natural generalization of Hitchin type systems. Change. Okay, I'll send you.
Yes, please. Thank you.
The reference. Okay. More questions? Okay, then, Taras, thanks a lot. And
Thank you.